Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I have the pleasure of introducing Sandeep Gupta, who is a professor at Arizona State University in Tempe, and we met at the NSF Cyber-Physical event, and he has done interesting work in applying sensor networks and cyber-physical computing to diverse areas, such as healthcare monitoring and data center thermal monitoring, which is what I believe he's going to talk to today. And then there are a number of other issues, other areas as well, which, maybe there will be an opportunity to talk offline. So I'm excited to hear about these, the healthcare and thermal management. So please.
Thanks, Johannes. I'm very excited to be here at Microsoft Research. So as Johannes mentioned, we are in Impact Lab. We do various work besides pervasive health monitoring and data center thermal management. And this is just a brief slide on other stuff I have done, like we have a book on mobile computing, and there's some conference we organized on body nets, which just got over. And we have a series of conference called GreenCom, which we want to advertise here. So you could look forward to that. So I come from Arizona, Tempe, not Tucson, just to make sure that I'm from Arizona State University. People confuse sometime. And this is and we do have water there. It's not that dry. Just want to bring that up. And this is just our building. Here are our current students who did all the work, and which I'm going to talk about. They view this as a mafia gang and use those terminologies. I have a person, I think Gianni. He's from Greece. Italy, and Georgios is from Greece, and they come up with this interesting way of looking at a research team. So today's agenda is, as the talk suggests, I'm going to talk about a dependable and sustainable cyber-physical systems. And cyber-physical systems basically are at the intersection of computing systems and the real world, right? And a lot of interesting research are going on, and these are just the two research I'm going to focus on today. So safe and secure pervasive health monitoring and green data center management. And I think you don't need much introduction to this and don't need much convincing that these are important topics. But let's see. So focusing on pervasive health monitoring, you can use sensors, body sensors, to monitor person's health. And you could collect all kinds of data, personal data, and security becomes an important issue, right? Because you want to protect that information, and then one can imagine various kinds of attacks in this domain, which is akin to attacks on the internet, and so one needs to come up with schemes to protect this healthcare data. With this regard, you can think about two things: the medical devices which are on the body, right, and the health record information which is lying somewhere on some server, right. So there are two aspects to it. Medical device market, as people might be aware, that it's a rapidly growing market. It is expected, or was, $75 billion in 2005, and is growing. And there are various categories you can think about: physiological monitors, actuators, for example, pumps, analyzers, devices like ventilators and scanners. So these are like heavy duty things, and these are more on body kind of devices, right? And what's happening is, as everybody knows, everything is going wireless and everything is getting connected, and people want it cheaper and things like that. You want to use cheaper components, commercial of the, and you want to basically have a plug and play functionality. But as we know that nothing is plug and play, right? And there are a lot of problems at the when these devices get misconfigured, and especially in the medical domain, you want them to be easily configured so that elderly patients and elderly people living in home can use them. Safety is also a concern besides security. So till now the focus mainly has been on safety, where you want these devices to do no harm to the people using those devices, right? And so a lot of work has gone into, like, for pacemakers, right, how to make them safe, and then for in future you want to have them secure, because as these devices become more prevalent and more people start using, like everybody now has cell phone, we can imagine a future everybody is wearing some kind of medical device to monitor their health continuously, right? And you want to make sure that these devices are safe as well as secure. And I'll give you an example of so there's some researchers at University of Washington, Seattle, who basically showed that the current defibrillator can be hacked into. Okay, so it's a recent research which basically FDA took very notice to, and they are very concerned about it. So with regards to electronic health record, which I'm not, the focus of the talk is not as much on electronic health record, but just I put up this slide to show that this is a important issue which is a lot of big companies are dealing with. I think Microsoft is every big player in this domain basically is looking into health record, electronic health record, right? So so let's quickly move on to pervasive health monitoring systems, which I've been hinting towards. You have all kinds of sensors. You could have a gateway PDA, all networked. You could imagine even the sensors inside human body, and there's already a lot of labs, like this is a nanoscale blood glucose level detector at UIUC they have developed, and there's this life shirt which is from some company, and you have from, this is from Matt Welch's group at Harvard, wearable pulse oximeters, and for, right. So this is all there, which will become more and more sophisticated. They will become low powered, more wirelessly connected, and things like that, right? But they enable healthcare monitoring with no space and time limitation, in the sense that you can be monitored anywhere. You're sitting in a talk, you're getting monitored, and you have some problem, people can take notice of it beforehand. So make it more proactive rather than reactive, right? Hopefully the quality of care will improve, right? Early detection of ailment is possible, and in case of emergencies, it can be like if there's a fire in the building and a lot of, or there's a terrorist attack, a lot of population is affected. This kind of technology can help in automating the because there's fewer. So what's going on in China, right, currently as we talk, as we speak, right, or what happened in Myanmar. So in those situations where you have catastrophic situations due to earthquake or some flooding, like Katrina, this kind of technology in future may be of great assistance. So in general, in this country, the population basically is aging pretty fast, and baby boomers are aging, and they want to have independent living, and this technology can have help towards improving the elderly people to live independently. So basically, there are various kinds of applications possible, as I hinted, and what we want to go from currently manual, slow, costly, and inefficient way of doing things to automated, real-time, inexpensive, and very efficient. So we want to transition from here to here, and we want to use this pervasive technology to help us. As a system architecture, you could imagine a patient with all the sensors. You have some management plane, a knowledge generation place, and on the other end, the healthcare provider is there. And you want some kind of feedback so that this operation can be efficiency of this, of effectiveness of the operations here, or functionality can be improved. So you have something kind of feedback, adaptive system, right? So you could imagine all kinds of things, collection of data, processing, where to process, how to efficiently actuate, storage management. And one thing is of context, right? So you want to make this context aware. You want to personalize this. You want to, so if you want to be aware that a person is jogging, or person is had a meal recently, and things like that, so that you could respond. Because suppose you are monitoring a diabetic patient, right, but the person has a meal, that blood sugar is going to shoot up, and that is not a problem usually, right? And so you have to be context aware and take into account various kind of both physiological as well as ambient sensing information. So you want this management plane to be context aware. Okay, so adaptive and context aware. So overall, there are various issues which fall into category of hardware, software, regulation, standardization, and obviously, when we are talking about medical healthcare things, who is going to pay for it, right? That's one big issue. Who is going to pay for everything, and who is responsible for it if anything goes wrong? So there's the regulation and liability issues, legislation issues. Obviously, we are focusing on kind of software issues, and we will want to get involved in standardization and other things. But in the software, basically, we are looking into reliability, energy efficiency, security, fault tolerance, and context awareness issues. Okay. So I'll quickly talk about some safety things we have worked on, and then some novel security solutions we have come up with, and we are trying to integrate in a test bed called Ayushman. It's a Sanskrit word. It's a blessing for long life in Sanskrit. So since you like to learn many languages, this is a kind of new. I don't know whether how much Sanskrit you know.
Sound like mafia.
So one issue we thought about is, suppose we are going to implant a lot of sensors. We can think about a network of sensors within the human body. That's where we started. And one of the way things happen in a sensor network when a lot of nodes are involved is you do clustering, some kind of clustering, and you have a cluster leader. And basically what happens is all the communication, long distance communication, takes place through the cluster leader. So if the cluster leader is going to do a lot of work, then it's going to dissipate a lot more energy than the other nodes. And so basically the issue is, if you deploy a system, you want to make sure that the amount of energy dissipated doesn't harm the tissue around this cluster leader. Okay, so there's a very simple problem, maybe a hypothetical problem, but just we got started, and we came up with some interesting solutions. So I just want to talk about it. And let me give you a little bit context. We had a NSF project on retina prosthesis, a chip with this array of probes, which basically you have an external camera and you basically stream some signals to these probes and activate these. And that's how we got motivated that in future you might have a dense sensor network for some prosthetic purposes. Whether in eye temperature is a problem, because if you raise the temperature by even 1 degree, the chances of infection increases dramatically. So some parts of the body are very sensitive to temperature rise, but in general, if you want to convince FDA or somebody, you have to model how safe your device is, how much energy is dissipated in the body due to these devices, and make sure that it is well below these safety limits, right? So we modeled it as a problem in electromagnetic radiation absorption. So this is the control volume sensor, a cluster, a leader, and we also imagined that since there must be some powering source, and one way to power is through RF powering, and so we took that into account so that these are periodically charged through these sensors through RF powering. And then we came up with some basically differential equation which captures all the heat accumulated due to various sources, like through radiation, through heat transfer due to blood flow, to the circuitry of the sensor and the metabolism, and all basically put them together. And then this equation can be solved through the normal techniques of FTDT, finite difference methods. And basically one thing what we did was if you use the normal FTDT enumeration method, before I go into that, I need to just clarify what the problem is. So what we want is to find a sequence of rotation of the leader. So suppose this is a 5-node network, right? And here is a sequence. So node 1 will be leader for some time, then node 3 will be the leader, then node 5 will be the leader, node 2 will be the leader, node 4 will be the leader. That's one sequence. Another sequence may be 1, 2, 3, 4, 5, and you rotate like this. And you could come up with various. So this is like a traveling salesman problem, right? A classical computer science problem, which is NP hard. But this problem seems to be harder because when node 1 is the leader, the temperature around this neighborhood increases, and the cost of this being the leader increases. So it's dynamic. It depends on the past history. In traveling salesmen, all the costs are static, right? The distance between the cities are constant. It doesn't matter which order you take that.
So what you want to do is to minimize the heat in some certain areas. You want to
in any area
as much as possible.
Yeah. So basically, you want to. It's a load balancing kind of problem. You want to balance it out so that the heat in any portion of the tissue doesn't rise above a certain threshold, right? Or in this case, we are trying to find the maximum temperature which any point in this area can reach, right? And so if that is maximum is below the threshold, then you are safe, right?
So how far does the heat travel?
So the tissue basically is a property of the tissue. So different tissues have different conductivity, right. And then it's a property of the blood flow in that region, right? So that's why we need to take into account all those things, right? So but in general, you know how heat propagates through conduction, convection, and things, right?
So how? What about this when you put power then with RF through the tissue? How does that work? I mean,
so you have to take how long you are powering, how much the strength, signal strength, powering, and how much energy is absorbed during that powering. So you take that into account. So it acts like a capacitor, right? So you basically charge it and then it dissipates over time, and so you take this into account how it is dissipating through the various mechanisms. So you take into that into account too. So that's taken into account.
Yeah, because there's a lot of water, so it seems like
absorption is there, right?
There will be a significant absorption.
Yes, yes, yes. So that's why you have to. It's not body is can be imagined almost all water, right? Right. Saline water. So that's a good model for a body. Just view it as a saline water, concentrated saline water. So for various, from the computer science aspect, like you want to find a fast method. So basically, if you do the FTDT method, it will take a lot of time. We applied genetic algorithm to brought down the time, but then we came up with some heuristic technique to basically, along with genetic algorithm, and for a decent sized network, we could find a near optimal solution in minutes. Here on this scale, you can see like this is the variance of the temperature and the mean. And for various kinds of solutions, like a dynamic solution, which like a greedy solution, or this is the optimal. So what you want to do is to minimize the variance, keeping the average constant. Okay, and so basically you could see various solutions give. So here you want this TSP solution, which is a heuristic solution, which is basically takes into account the spatial distribution of these nodes as well as the temporal sequence. So it takes into account both the spatial and temporal, and which we call the space-time function. And basically, using that, it can quickly come up with using genetic algorithm technique. It can come up with a near optimal sequence. We extended that to what if you want to route a message in this, if you have a multi-hop network, and what if there's a hotspot in the area. So we came up with a very simple technique for backtrack based routing. So basically, when you hit a hotspot region, you backtrack and try to find another route. Again, how useful this is for future network, only future will tell. But this is just a new way of looking at problems in cyber physical domain. Okay, where the main issue is that what you do in the computing domain, right, routing, has an impact on your surrounding, and the surrounding has an impact on your the strategy you take, right? That's the cyber physical nature, and that's what we are studying, right? The problems may be like dining philosopher's problem. They are toy problems, but they help us to focus on some techniques, and this is kind of those kind of problems.
And it is kind of cute that hotspot actually is literal.
Yeah, it's a literal hotspot, right? Yeah. Another issue which is that, okay, you want to do communication, what is the best coding? This is more into the electrical engineering domain. We came up with a physical layer coding scheme, a source coding scheme, where basically when you can trade off bandwidth with energy consumption. Okay, you come up with codes where you have only one. So this is whenever energy is consumed only for transmitting one, and so basically you are trying to minimize number of ones to be transmitted. Obviously the code length has increased, so the bandwidth consumed is increased, but you could achieve same communication in lower energy. So this is one technique we came up with to do communication when you want to minimize the dissipation of energy during communication. So I guess from the computer science perspective, information security is of greater importance, and so let's move on to that. So you know that security, for securing communication, you need to do either symmetric key or key-based cryptographic based techniques. There are non-cryptographic based techniques too, but let's focus on cryptographic based techniques. So what we came up with is idea of how to avoid key distribution, or how do you do key agreement using physiological values. And basically the problem is there are two sensors who want to communicate with each other on the body, and they want to do it securely. How can we generate these keys from the physiological values? Okay. So what we want is something opposite of biometric. Biometric is something is a characteristics of a human which doesn't change with time and is unique. What you want is something for the keying purpose or cryptographic purpose. You want it to be time variant, not time independent. You want it to be universally applicable. You want it to be distinctive in the sense two persons, if you generate a key, they should be very much apart from each other. And you want fast methods, low latency methods for real-time communication, and as I said, time variant, right? So this is a different problem than the problem of biometrics. Okay. So advantage is that it's easier and safer key generation, hopefully reduce deployment cost, and enable plug and play for body sensor networks. So as I'll show that we have come up with two physiological values, interpulse interval and EKG, which we have demonstrated that you can generate cryptographic keys, and we are looking into finding other PVs. So let me just quickly go into this. So interpulse interval, basically if you have gone to doctor, you have seen this EKG signal, right? And there's this this is interpulse interval between, and then there's a PPG which also has that. And basically if you take two different persons and if you look at the stream of interpulse interval, they are very much apart. So you could take that and basically come up with some method of generating a bit string from these two, and a bit string from here, and use that, try to use that as keys. So if you look here, we took some data from some MIT physiological database and generated keys, and there's a between the same persons interpulse interval data, the Hamming distance is basically very, very small. But if you took say S1 to S2, the Hamming difference or distance is 80 to 90 bits or more. So basically you could use it as an authentication scheme, at least this one, that this, if you two nodes try to have bit strings and they match within 10 bits, the Hamming distance is less than 10 bits, they are from the same persons, though both sensors belong to the same person. So this rudimentary scheme can be used for authentication. Okay. But we want more. We want this Hamming distance to be 0, right, for the cryptographic keys.
Does the stage or the health of the person affect these measurements as well, or?
No, because this data was from various people in this MIT database, different conditions. People have different conditions. You are measuring this at the same time, as I say.
I see.
Okay, both nodes, there is some synchronization involved. They were measuring the data at the same time, so or nearly in a synchronized manner. Okay, so yes.
Does the location of the sensor in the body have anything different how it senses these various things?
There might be. We have not gone that far in our research, but this is just getting data from a database. Now we are actually deploying these sensors and trying to do it, implement it. So within 6 months maybe we'll let you know whether it actually works on a human body or not. But this is just a proof of concept test, test from the recorded data.
But essentially, you could use then also this as a fingerprint, that you could measure somebody's heart for a little bit, and you could recognize that this is the same person.
Well, that is a different research that people have done on signatures from heart, which you can uniquely identify. So that's why for that it has to be an external entity is trying to verify your identity, right? And so you want something which doesn't change with time, right? So that is a different problem. That's a biometric problem.
Right. Okay. But these are essentially what you're doing is that you take two different measurements of the same thing and then you correlate them. Can you explain again how does that solve a cryptographic problem, or
okay,
how do you use it? I think we are.
Okay.
I'm confused anyway.
Let me go into this. If it doesn't get clear, then I'll come back to your question. Okay. So you have imagine two sensors, right? You have some way of synchronizing them, and we have come with a secure way of doing that. Then you measure for 5 seconds, and at a sampling rate of 125 hertz. Okay, so this is for the I think EKG. Okay, this was recently published in a mission critical network workshop with Infocom. And then you have this key generation. Basically, you do frequency domain analysis. You do feature extraction of 640 coefficients. Then you quantize them into 20 blocks. Then you exchange the hashed blocks, and then based on which hash values match, you can go back and get those blocks, and then you could concatenate them into a key. So that's how it works. Okay. So this key is never in clear. It is in hashed form on the channel. There's some communication involved to exchange this hash blocks. Okay. Does that answer your question?
So essentially, this is where you have two sensors within the same body, and this way they can create a shared key by essentially modulating the signal on the heart rate.
They're not modulating. They're analysis. They're doing analysis. They're extracting features. We have frequency domain features here, basically frequency component features, and then using some of those components, trying to agree on them by exchanging some hash blocks, and then generating the keys, which are exactly same.
Okay. So essentially, I couldn't, because there is the communication, and if I were monitoring from the outside your heart rate, for example, which I think I could do remotely with a laser, for example, see how your finger is moving, then I couldn't still generate the same key because I didn't participate in your kind of exchange. Or could I actually, from the outside, find out what your key is going to be, and that way listen to it? I mean.
Yeah. So So when you exchange this hash block, it is a hash value. So you really don't see this. What was the measured value? The other thing is you have to measure at the same time as these sensors measured. Right. That is one thing. The granularity of measurements will be different because remote monitoring doesn't give you that granularity, good granularity of data. So it is all dependent on a lot of other factors. And so basically what we think is, this is pretty secure in the sense the remote monitor cannot generate the same key.
So essentially you have to both listen to the
at the same time
or the traffic, and at the same time
and
monitor the heart.
Yes,
pulse.
And be able to extract the same components, right? So
but that you should be able to do because the algorithm can be assumed to be known. Right?
Oh, well, see here when you are exchanging these blocks, some blocks match and some blocks don't match, and the blocks which don't match. So between you throw them away and you just take the blocks which match, take that index and then go back to this and get the actual block from the, not the hash one, and concatenate them into generating the key.
Okay. Well,
okay.
Interesting. Yeah, looks good.
We basically use that same database, and basically there were 31 subjects, and basically this is the Hamming distance between the key generated. This shows Hamming distance quite same, and this is like 60% apart. Now you can see that between the same persons, it's basically 0 Hamming distance. It's all black. Between any person, this person with any other person, you can see that there's 50 to 60% keys which are bits which are different. We also did like entropy kind of analysis, finding how much entropy, and kind of you could see like it's a 99 average of 9.99 kind of different some cases. So it shows a promise, good promise of generating good cryptographic keys. So as I was saying, recently Halprin and Ransford, Head, Benjamin, and these are all from University of Washington, I think. What they did was they took the pacemaker and a programmer. There's a programmer, you program this pacemaker. Basically what they listened to the communication and basically broke it, and then through some kind of playback attack kind of they were able to reprogram this ICD into giving a shock to the generating a shock. Okay, they didn't do it on actual person, but they were able to break into it through reverse engineering and things like that, and measurements. So basically what I wanted to point out is, I think this, since we are running out of time, just what I want to say is that we could use the similar PVS based scheme. So have the ICD is already on the body, and the programmer is connected to attached to the body if it is placed on the body, and if they are able to generate the same key, then you could secure the communication, and you are able to avoid this kind of attack. What was happening is some of the communication which was taking place in the previous way was in clear channel, and so it was not encrypted. Also the problem is you could have pre-deployed keys, right, and pre-deployed keys may solve that problem, but again pre-deployment has its own problem, right, as you know. So this avoids pre-deployed keys and is able to secure the communication. So that's what I wanted to get across. Any questions? Right. So since we have only a few minutes, 15-20 minutes remaining, I want to finish it and move to data center thermal management. So what we are doing is incorporating this into a kind of Eichmann testbed, which basically has a kind of same system model where you have body sensor network connected to a gateway kind of, then there's through internet it can be connected to external gateway, and through or basically through internet it can be connected to the medical professional. So we have come up with a kind of a middleware kind of thing, which basically has all the components like context generation, service discovery, context interpreter for physiological point of view. You have security services, and basically all geared towards medical monitoring. Okay, so this is may seem like generic, but we are focusing more from the medical point of view, so that solutions like the one we talked about are incorporated, and security is built in the system from the as an integral part, not as an add-on. Okay, so the goal is to make cheap and efficient, secure systems for medical health monitoring. So this is the current setup. Basically, it's going to be demoed at HealthNet conference in Boulder, I think Boulder, Colorado, on June 15th. So this just shows the current interface where you could, on a PDA, you could look set up which sensors to monitor, what you could query, and you could set up alarms and things like that. This doesn't look very wearable, but as you know, the technology is improving. This is just our proof of concept thing. Okay, so so this part of the talk I was focused on cyber physical nature of pervasive healthcare, and tried to convince you that there are a lot of interesting problems in this domain, and we have solved some interesting problems. What next I want to talk about is data centers, which is very much far from this, and thermal aware scheduling, but this is again we view it as a cyber physical system and try to come up with some novel solutions.
It will be interesting to see if the same algorithms apply in your previous thermal awareness.
Yeah, we have I didn't bring that slide. I gave that talk where I can show you offline that there's a lot of similarities. Yes?
My colleagues doing election protocols have a concept called the receipt-free property, which may apply to healthcare. Basically, you want your doctor to see your real data.
Yes.
And the bossman comes, sign here that I can see all your data, right? And on some election system, you can make the bossman see whatever you want him to see, right? And the doctor sees what he should see. And it takes some interesting planning to make it work right.
Okay, okay.
Because, you know, once documents exist, bigwigs will insist on getting them and even force you to sign that they can get them.
Thanks. Yeah, I'd like to see those things. Yeah. Very interesting. So in the domain of thermal management, there's currently everybody's talking about multi-core, and there are things are happening in multi-core domain. And there are recently there's work on scheduling the cores on a multi-core system for thermal management and all that, right? Which if you pick up any PAL computing conference, there is sure to be half the papers on multi-core and all the issues, right? But data center operations is at much larger scale, and there are some similarities, but as I'll point out that thermal management in data centers is much more cyber physical in nature and needs a new way of doing things. So there's a lot of work in temperature aware, power aware computing and management. So these technologies are currently being used in data centers, but what the point is that these technologies are mostly reactive, right? Like at chip level, if temperature goes up, you throttle down the CP. When it overheats, basically you lose performance, right? So you react to it. At chassis level, there's also you can shut down when the power unit draws more current than it is supposed to, and when temperature exceeds. And there are other techniques at room level, but all these reactive mechanisms cannot effectively mitigate the sources of overheating and have the potential to lose performance or reliability. Okay. So what we want is proactive and predictive mechanisms, and that's what we are trying to develop. So just to show you why a data center is cyber physical system, so it's a cyber physical system can be a computer system that is coupled with its immediate environment, as we saw in the medical domain. Here also it's same thing. The operations of the computer system affects the immediate environment, causes this thermal flows, and these thermal flows or heat exchanges within the system basically impact the performance of these systems themselves. and so this we view it as a cyber physical system where there are close interaction between the environment and this computing system. So what we have done is things like power profiling of these systems and come up with some linear models to predict power consumption given a particular utilization of the system. We have come up with predictive thermal models for data centers. So basically, given utilization of the systems and the layout, what kind of temperatures you will see in a data center. What I want to point out is that there are CFD based techniques which will take hours and hours to come up with this solution and maybe more accurate solutions. What we want for real time scheduling is this prediction should be very fast so that you could do scheduling in real time. So that's why we want analytical thermal models for online scheduling, and we have applied some machine learning techniques to doing that, as well as trying to model it as a linear optimization problem. Then we have come up with some scheduling techniques, and I'll show you that there is some performance improvement you can get by applying these scheduling techniques. We are coming up, we have incorporating them into software architecture which we call DoCool, and we are testing and validating it, and we actively involved in the community through GreenCom conference. So to give you a quick idea of what goes on, consider a node in the data center. A node is basically can be a chassis here with a blade server. This is a blade server, right? We consider a node which has its own inlet and an outlet for air. So that is the granularity at the inlets. So that is a node, and basically we try to model this nodes. What is the temperature? We try to predict this temperature T in and T out. So what happens if this node generates some heat? Some of the heat generated goes to the AC unit. Some of it impacts other nodes in the data center. This depends on the design of the data center, and so for a given layout and a design of a data center and placement of AC units, you could compute these coefficients of heat exchange through some profiling, and then once you have this, you could incorporate that into a linear model. I think this is the run out of battery. Okay. So that is this is the matrix D, basically captures this interference, and then given the power utilization vector, you could and the T supply temperature, you could predict the input temperature at each node. So basically, the scheduling affects this power. So given a job and its allocation or a scheduling, which we call task placement or task scheduling, you could compute what will be the impact on temperature. What we want to do is minimize the maximum temperature. Okay, so basically you apply a genetic algorithm using this model and try to come up with power vector which minimizes the maximum temperature, inlet temperature. So that's the basic idea. Okay. To apply a linear model, you have to, the system should be nearly linear, and we did some power profiling on Dell systems, and basically for a different disk IO rates, basically as the CPU utilization increases, the power consumption almost linearly increases. There is some differences at different IO rates, but it's almost linear. So basically, as I mentioned, you could use this power profiling into converting this P vector into utilization. So convert it into utilization form with linear factors A and B. These are characteristics of the machine which you are employing, and this is the utilization. And basically now you could basically directly plug in instead of playing with power, you could say, okay, if utilization of this system is this, and depending on that, what is the T? So you have moved from power domain to utilization domain. Okay, and that is very useful in scheduling, because when a job arrives, you have a task profiled with respect to utilization, not power. And so once you, then it makes it easier for doing job scheduling rather than. So all the previous work stopped here. They used to deal in the power domain, but that's not very useful for scheduling. So this is like the second contribution, like formulating it into fast problem and then moving to the utilization domain. Now cool data center operation, that's what it do-cool stands for. So basically we are incorporating this into kind of data center management framework, whereas a coordinated predictive controller, you model the arrival patterns, a data center model, and the data center thermal model. You have the equipment model, and you have the monitoring of the equipment load, and all this can help into job scheduling and placement, which affects the power controller, also coordinate the power controller and the cooling controller, and basically try to minimize the combined energy consumption for the computing as well as cooling. So as you know that if you look at data center utility bill, you can split into half goes into computing and half goes into cooling, right? And so, but what you want is the combined. So some people only focus on this, some people focus on this. What we want is the total utility bill, which is the real money which goes out, that to be minimized. We have done some simulations using Dell PowerEdge 1955 and 1855, and we have a scheduling algorithm called Accent, and basically there's another one called MinHR, which was developed by HP Labs and Duke University, and we are comparing with that, and basically at various CPU utilization rate. So at a very high utilization, like 100%, there's no difference, right? Means there's no flexibility of moving tasks around or doing anything. And so what you do, benefits you get is between 20 to 80% of utilization, and this one, let me. So if you do combined cooling and computing optimization, you could get slightly, in this case, slightly lower utility cost or power consumption, if as opposed to if you only try to minimize, I think, computing. And so this is a very small scale example, but you could at least here like 2 to 3% savings, which is, if your utility bill is in millions of dollars, it does make a difference that you are able to reduce 2 to 3%.
So this is because some computers are more power, or you get more computing per the power.
So you have to look into their computing profile, right? Power consumption profile. Also you have to look at where they are placed in the data center and what impact they have on the neighboring systems. Okay. Right? It's a combination of those. Right? And when you combine all those, you may be able to get a larger savings rather than just trying to. So take two systems which are of same capability, but one is placed in a good location in the data center, one is in poor. If you don't take that into account, then you would obviously it will be poorer scheduling decision.
So a good place would be something that's spread out evenly?
Well, heat goes directly to the AC unit, right? It doesn't impact. So a lot of it goes into design, as my next slide will show you. That here you could, it is trying to give you an idea of what kind of optimization helps how much, right? So this, at the lowermost, this is the theoretical best you can do, okay? This is the with no optimization. So you can see there's a big difference. And if you do, so this one, if you only minimize the computing power, then you can come down to this. If you minimize the recirculation effects, then you can come to this. Saving by turning off idle machines, you can come down to this. And then there's some unaddressed research issues which I were working on. But even in the best scenario, you could see that this is due to the design of the data center, right? So there's a physical design issues which can bring this down, but the computing and scheduling can only bring it to this level. So that is what it is. So there's a combination of, so you have to think about whether you are going to spend, how much money you are going to spend in designing the facility, as well as how much money you are going to spend in the operating it, and the total cost. So that's what we're trying to capture, right? You can design a very high-tech data center, but whether it's worth it or not, right?
Then you should estimate what kind of load you're going to have.
Yeah. So it's always a function.
Load, it doesn't matter.
Yeah, low and high loads. Usually data centers operate at 60 to 80% kind of. That's the normal operating range. A well-designed data center, I guess. So this is just kind of scratching the surface. There's a lot of work which is going on. We are moving into how we can take into account task heterogeneity, equipment heterogeneity more efficiently into making better decisions, better integration of cooling and power control, how we can use machine learning techniques to avoid profiling. Nobody wants to shut down their data center for profiling. How can you automate profiling using some machine learning techniques, and how we can incorporate these techniques into systems like Moab and Slum, which are used in commercial data centers. So there are some publications which we have if you are interested in. So any questions? That's, I guess. Yes?
If you return to your last multicolored slide,
yes,
it looks like what 80%, if you call your 80% 100%, in lots of industries you'd say, 80% is normal engine. The 100%, your 100% is what jet fighters call afterburner.
Yes.
It's, emergency power. And now I don't know how big is the fixed cost. I mean, I have a chart with the variable costs. Now, the fixed costs are as big as this rectangle, or twice as big, or 3 times as big, because the machines cost money and the center costs money.
Yes. So I don't have that answer because it depends on various factors. But there are surveys which have been done. There are a lot of reports which have been written. I'm sure there's one on the ASHRAE. There's a ASHRE. They print a lot of reports on data center. A lot of from mechanical engineering community, like I know people at Georgia Tech and other places, which from that community they are doing a lot of work from the design perspective. I being computer scientist, I thought, okay, that is not my domain. I would focus more what we can do in software.
But if fixed costs are 10 rectangles, I don't care. If the fixed costs are 1 rectangle or half a rectangle, I say above 80%, you are pulling out the stops and handling an emergency. And I just don't know what the fixed costs are.
Okay.
But there is a time delay also. I mean, you might plan it on
But money is money,
60%,
right?
and then
Yes.
your product
Understood.
is more popular, and
Yes.
then you have to run it at 100%
Yeah.
while you are buying new computers.
Yes.
I mean, that could happen. So,
Yeah.
Well, yeah, your demands can shoot
yeah.
unpredictably.
Yeah, because there's a huge delay in buying new equipment and installing it, and you know, if your service is successful overnight, you might be in trouble meanwhile. And
So what
you're
are-
blowing the fan?
Oh, yeah.
What people are also talking about is all data centers. One is putting them together, right, through virtualization, trying to consolidate them. The other is linking them together. One data center is overloaded, you try to distribute it over various data centers. And what if there's some earthquake or something and one data center goes down, right? All your load moves to. So there are a lot of issues, yeah. So you have to take that into account in your global strategy of making data centers. So this.
And it might even depend on weather. You know, if you're a data center that's in a very hot place, it must be more expensive.
No, all the data centers should be in Iceland. That's what I feel. Or in
Maybe everything.
so, but there's another issue there, right? If you put everything, all eggs in one basket, then there's a problem in that too. Yes.
Well, Iceland also has much cheaper power, so that's
For now, right? But what will happen in future?
So they really don't pollute.
Yeah.
So that's kind of the point, right? If you can keep your data center utilization at like 60 to 70%, you can solve all of these in software, right? There's almost nothing to be gained by future redesigning your data center, as long as you don't go above like 70%. That's
Yeah.
kind of the point of the slide.
Well, I didn't think about it. Yeah, you could get very close to software. But again, this is kind of a more from a modeling point of view. We have to validate this through actual implementation in data centers. So our models may not be that accurate. So you have to take it with a large pinch of salt.
Right.
Yeah. So, yeah.
Okay.
Okay. Thank you.
Thank you very much.
Yeah.